All right, let's get started. Hello, everyone. Welcome to CEEE688, the Advanced Concrete Technology class. Okay. So first, let's introduce ourselves. For me, my name is Lin Shen. I think several of us know me already. So I'm an associate professor at UH. My office is 344 Holmes Hall. Okay. So here's my telephone number and email address. A little bit of information about myself. I joined UH in 2011, almost 11 years ago. Okay, and my research focus is on concrete. Okay, so everything related in this course, so I do research on it. Okay, so for example, sustainable concrete, SCC, geopolymer concrete, and so on. Okay, so before we go into the details information about the class, let us introduce yourself. Okay, so what is your name? Whether you are graduate students or undergraduate students. I know some of us are undergraduates maybe, or you are from BMA or Bachelor and Master, which is the fast track or 4+1 program. So I'm the program coordinator for this semester too. Okay, who is your advisor? What is your focus on? Structure, transportation, geotechnical, and so on. And anything you want to share about yourself. Okay, so David, could you introduce yourself to us?
Sure. I'm Dave Nixon. I'm a master's student in structural engineering. Professor Robertson is my advisor.
Okay. All right. So welcome, David. Marisa, could you tell us something about yourself? Hi.
Hi, my name is Marissa. I'm currently an undergraduate student doing BAM. I haven't chosen my.
Okay.
Yeah.
Okay. So this is your junior or senior?
I'm a senior right now.
You're senior already. Okay. All right. So that's the first year for BAM.
Yeah.
Okay. All right. Okay. Thank you, Marissa. So next is Dana Park.
Hi, I'm Dana. I am a master's student and I'm concentrating in structures, and my advisor is Dr. Robertson.
Dr. Robertson too. Okay, so you are regular master students. You are not in fast track. Okay. All right. So next, let's see, Joshua. Joshua.
Sorry about that. Okay,
Yes.
So my name is Josh. I am a BAM student. This is like my second year in the BAM because they don't offer enough structures classes, but I should be graduating this semester. And my advisor is Dr. Cho. And with Dr. Cho, I'm an RA for him as well.
So you are a research assistant for Dr. Cho?
Yes, I'm a research assistant for Dr. Cho.
Okay,
yeah.
Good. All right, thank you, Joshua.
You're welcome.
Okay, Jake.
Hi there, my name is Jake. This is my second semester of my master's program, and my advisor is Professor Robertson.
Dr. Robertson too? Okay,
Yep.
All right. Okay, Jake. Who else? Let's see, Chandel.
Hi, I'm Shindel. I'm in my second semester of a BAM program, and I'm researching under Dr. Oceana Francis for soil erosion for our coast along Hawaii.
Okay, nice, great. Okay, who else? Okay, Jian Xin Huang.
Hi, I'm also my second semester of BAM, and
Okay.
my major is structural engineering with Dr. Robertson.
With Dr. Robertson too. Okay, a lot of BAM students. Okay. All right. I think who else? Scott Lam. Can you open your microphone? Scott? Okay, Scott made.
He just messaged that his, he just put a chat that his microphone doesn't work.
Okay, I see. So Jonathan?
Hello, I'm Jonathan Hargraves. I'm a first year, second semester master's student. I got my undergrad here at UH as well.
Okay, all right, okay. I think I know many of you, and you know, I see quite a few of you coming from the BAM program. Okay, so as I said, this is my first semester taking over the BAM coordinator position. So a lot of things I need to learn from about this program. Okay, so let's get started. Let's open the syllabus. Look at the syllabus. All right. Okay, so this is the syllabus. Anybody can see it?
Yes, we see it.
Okay, great. So there's some office information. All right, about the classrooms. So everybody knows for the first 2 weeks, we'll be doing online classes. So using this Zoom ID, so 95580967889. So that's no password. Okay. After that, you know, depending on the most updated policy, we'll go into the Holmes Hall 248. So this is our formal classroom, second floor in Holmes Hall. Okay. So meeting time Tuesday, Thursday, 12 to 1:15. Office hour, I think for this semester, if you want to see me, you know, let's make appointment from Zoom. Okay. So topics covered in this class mostly will be related to cement and concrete. So we have 2 parts. The first part is called concrete technology, which is meaning about what we learned already from CEEE688 if you take that class from me as an undergraduate students. We talk about concrete constituent, composition, property of Portland cement, the cement chemistry, the hydration of Portland cement, microstructure of cement, property of sand and coarse aggregate, and also admixtures, including chemical and mineral admixtures. Okay. For fresh concrete, we talk about how we can measure the slump flow, air content, and other properties, and how to design a concrete mix, and how to prepare the concrete mix, transportation, placing, and cure the concrete. For hardened concrete, we'll study the stress and the strain behavior, fracture mechanics, fatigue, how to evaluate strengths and other mechanical properties, shrinkage and creep, long-term durability issues such as freeze-thaw, ASR, soffit attack, corrosion, and so on. And also retrofitting technology. This is something we haven't been covered in CEEE688, how to repair deteriorated concrete structures, specialty concrete, including geopolymer concrete, which is sustainable concrete. There's a lot of research involved with this type of concrete here at UH, and how we can design high performance concrete depending on the need. Okay. And the second part of this class is called non-destructive testing and advanced material characterization techniques. So we'll talk about NDT method, including ultrasound, ground penetration radar, and how to choose different type of method depending on the applications. We also study microstructure analysis techniques such as mercury intrusion, porosimetry, scanning electron microscope, X-ray diffraction, and the thermal analysis. So these are methods that are being used to study the microstructure and also chemistry inside the materials, not only limited to cement and concrete, but can also be used for other type of materials. The textbook, the title is called Concrete. The author is Sidney Manders, Young, and Darwin. This is second edition. I'm not sure if you can find it from the bookstore. If not, you can try to buy a second-hand book from Amazon, for example. I think for this textbook, you don't have to buy it for yourself. Maybe 2 or 3 of us can, buy one book together. That should be enough. I also have one copy in my hand. So if you want to have a look, you can borrow from me. The majority of the information will come in from handout. So before the start of each lectures, I will upload the PowerPoint presentation to Laurima, so you can download it. All right. So what else? So about assignment, so we have several homework, not too many, and also maybe 1 or 2 quizzes. We have 2 midterms, okay, 2 midterms and 1 final exam. So the midterm is 15% each, and the final exam is 30%. At the end of semester, we also have research paper and presentations. Okay, this is similar to what we did for CEEE688, but this time it is the individual research paper and individual presentation. Okay, so you need to write about 10 to 15 pages. The title should be related to cement and concrete research. Okay. So we'll talk more about this toward the end of the semester. All right, this is the tentative schedule for the class. Okay. So any questions before we start the formal lecture? Questions? Okay. Okay, so you download a free copy of textbook. Okay, that's wonderful. So why we should study the concrete? Okay, so the concrete is by far the most widely used construction materials. So actually, concrete is the most used man-made materials. Concrete is the backbone of infrastructures. It can be made, any type of infrastructure can made using concrete almost. Buildings, bridges, pavement road, you name it. So all kinds of infrastructure can be made from concrete. In the US, every year, we use about 2 tons for each person of concrete. Concrete has long service life. Well-designed concrete can last for hundreds or even thousands of years. Okay, concrete is also resistant to fire and also resistant to impact. Okay, the value of concrete is very high. The cost of the concrete is much lower compared to steel and aluminum. Okay, and the cost of repair concrete structures is relatively low compared to other type of structures. What is concrete? Okay, let's have a look of this short video.
Concrete is a mixture of Portland cement, water, and aggregates such as rock and sand. The aggregates serve as the filler material in concrete, while the Portland cement and water form a paste, which serves as the glue that holds the aggregates together. Through the chemical reaction called hydration, this paste hardens and binds the aggregates into a strong, durable mass we call concrete.
Okay, so the word concrete is coming from Latin word concretus, which means hold together, okay, or form rock. Okay, in the concrete, we have the most important materials is Portland cement. Okay, so why it's called Portland cement? We'll discuss that in a moment. So this is the glue, the fine powder. Okay, together with water, Portland cement will form cement paste. Okay, so that's the glue which hold other material together. Mix cement paste with fine aggregate, which is another word for sand. We have mortar. Okay, if we add larger stone, we call coarse aggregate into mortar and mix it, we have concrete. Okay, so in concrete we have cement, water, sand, coarse aggregate, any type of admixtures. It is not necessary, but it is very commonly used. We'll talk about admixtures in future lectures. Okay. So depending on the requirement for the concrete, such as the strengths, different concrete has different proportions of its materials, as we can see from here. Okay. Also, we have small amount of air, okay, typically around 1 to 3% by volume of air in the concrete. So the air is put in concrete either on purpose or not on purpose. Okay. For example, if we want to increase the concrete's resistance to freeze and thawing, we put some air. We call that air entraining agent to introduce the small air bubbles in concrete, so concrete will be more durable in winter time. The reason we put sand and coarse aggregate is a small and larger stone in concrete is one, to reduce the cost. Okay. The cost of aggregate is about 10% or less compared with cement. Okay, Portland cement is the most expensive materials in concrete, beside admixture. Okay, aggregate can also reduce shrinkage and creep of concrete. If concrete shrink too much, it may crack and reduce the strength and reduce the durability. So we put aggregate there, can also help to reduce the shrinkage cracking of concrete. Okay. And also it will make concrete less brittle, okay, increase the toughness of concrete. So here are some of the famous concrete structures. The Baha'i temples in Illinois, which is the pictures was taken near Northwestern University. Okay. The picture on the right is also called Baha'i temple. This is in Indian. The color of the concrete, as you can see, is white. It's made by white cement. Inside that cement, it doesn't have any error, so no error. Let's make the color white. Other than that, a typical concrete will have a gray color, grayish color. Okay. And the concrete is called formable rock. It can make into very complicated and delicate shape, as we can see from the picture on the lower left. Yeah. So this is one type of a precast concrete. All right. So some of the biggest concrete structures, this is one of the biggest bridge, is Millau Bridge in France. So the pier of this bridge is 250 meters or more than 800 feet high. Okay. This is one of the tallest building in Malaysia, the Petronas Twin Towers. So 1,483 feet tall. The tallest building currently is in Dubai, the Khalifa Tower. The height is 2,700 feet. Okay. The total cost for this building is 1.5 billion US dollar, and it has 165 floors. Okay, 165 levels. Okay. So as we mentioned before, concrete can use in road, concrete pavement, reinforced concrete bridge, reinforced concrete buildings, waste treat facilities, dams, nuclear reactors, subways, and so on. Okay. So this table compares the major, the important properties of concrete with other building materials. So concrete is in the last row. Okay. Compared with steel and aluminum. Okay. So concrete is lighter. So 23, 24, 100 kilogram per cubic meter. So steel is about 3 times of it. The strength of concrete is much lower compared with steel and concrete, especially for tensile strength. For compressive strength, which is in parentheses here. So a normal concrete has the compressive strength around 30 to 40 megapascal. Okay. So 7 megapascal is equal to 1 KSI. Okay. For tensile strength, it is much lower, about 10% of its compressive strength. So a typical concrete has a tensile strength of around 3 megapascal. Okay. Elastic modulus of concrete around 25, 30. Okay. Which is also much lower compared with steel. But the coefficient of thermal expansion of concrete and steel are quite similar. Okay. This is very important, because if the coefficient of thermal expansion of concrete and steel are quite different, we cannot really make a reinforced concrete in any climate with extreme temperature range. Okay, because in that case, we may have a debonding between the rebar, which is made by steel, and the concrete around it. Okay, so very good. We have a very similar thermal expansion coefficient between concrete and the steel. Okay, 10 and 11.5. For thermal conductivity of concrete, is very low. Okay, so that makes concrete a very good thermal insulator compared with steel. The fabrication energy of concrete is about 1% of that of steel. So that's one of the reasons why concrete is much cheaper compared with steel and aluminum. The cost of concrete is around 5% of steel. This table is coming from our textbook, table 1.5. All right, pros and cons of concrete advantage. So concrete can be made very durable, but if it's not designed very well, it can only last a few years. A well-designed concrete can last easily 100 years or even several hundred years. It is cheaper, economical. Concrete can be formed on site to any type of shape very easily. Okay, probably everybody has seen, concrete cast in the formwork and formed on site. Concrete is also energy efficient. Okay, it is a very good thermal insulator, costs less energy to make compared with steel and aluminum. Concrete is highly resistant to fire and thermal resistance. Okay, and concrete can also be made resistant to water. Okay, so we can protect the rebar using the concrete around it. But concrete is very brittle, especially under tension. Okay, so that's the major disadvantage for concrete, and that's why we use steel rebar in reinforced concrete structures. Concrete also have slow material development. A normal concrete will achieve its full strength after 28 days. But typically after 3 to 5 days, the formwork can be detached. Okay, so after 7 days, concrete will achieve around 70% of its final strength. But it has a slower material development compared with other materials. Still, we don't need any type of time to develop its strength. And also it has lower strength to weight ratio compared to steel. From on site, okay, we put it here both in advantage and disadvantage, okay, because it takes time for concrete to get enough strength. We also need to set up the formwork, and all this will take labors and time. Concrete is also shrink, may also have quick, so we call that volume instability. Okay. Too much shrinkage will cause concrete to crack. Okay, so concrete has been with us for 1,000 years. Okay, more than 5,000 years from ancient Egyptians. Okay, but ancient concrete are different from modern concrete. Okay, so around 3000 BC, ancient Egyptian engineer used gypsum mortar or lime with straw as reinforcement to make the famous pyramid. We'll talk about the chemistry about this ancient concrete in a moment. About 2,000 years ago, ancient Roman, they built the famous Colosseum and Pantheon using their concrete. Again, their concrete is different from modern concrete. All right, so everybody knows reinforced concrete. And why we put the rebar in concrete, we just quickly go over this. Okay. For a plain concrete beam without rebar, because concrete is very weak under tension, and under this load, the bottom part of the plain beam will crack very easily. Okay. So the moment resistance of the concrete beam without rebar will be very, very low. Okay. By putting the reinforcement in the tension area, okay, so we'll increase the moment resistance of beam much more. Okay, so steel is placed in tension area, but steel is easy to be corroded by water and the oxygen, so it needs to be protected by concrete. Okay, so steel is enclosed except for cracks. Okay, for steel to work efficiently, concrete must crack first, but that crack is very minor. Okay, for example here, but without any cracking, the rebar and the concrete cannot work together. So any type of reinforced concrete member, no matter how well it designed, must have some minor crack for rebar and the concrete to work together. Okay. Here shows us why we may use pre-stressed concrete. So here shows a typical bending and the bending moment diagram. Okay. The maximum bending moment is in the middle span, as we can see from here. If we put pre-stress, basically we put the rebar, which is in the bottom section, under tension before the beam take any load. Okay, so before the beam take any load, the concrete is under compression because the rebar is under tension already. So then we apply the load to the pre-stressed concrete beam, that will reduce the maximum moment in the middle span, and also we reduce the tension stress across the cross-section of the concrete. Okay. So that's the reason why we use pre-stressed concrete. So here is some of innovations in concrete for fabrication. We can use precast concrete. We can make the concrete very flowable by even pump the concrete. Shotcrete is also very a type of very flowable concrete. We also discuss extrusion, which is the method of fabrication can make the concrete into any type of shape. Self-consolidating concrete is the concrete without any consolidation. So that will accelerate the production process. Okay. So concrete needs some type of curing so it can develop its strengths. Okay. We can use typical curing, or can use high temperature, steam curing, or even microwave. Okay. We'll talk about admixtures, including silica fume, flash, slag. Okay. We'll talk about chemical admixtures, which can improve the performance of concrete, such as superplasticizer, air entraining agent, SRA, which is the shrinkage reducing admixtures. It can reduce the shrinkage cracking. We can use some special aggregate, such as lightweight aggregate or aggregate coming from recycled source. We'll also discuss special binding agent, not limited to Portland cement. Sometimes we can also use latex or polymer to enhance certain performance of concrete. Okay. Even for the reinforcement, we can use steel rebar. We can also use fibers, steel fiber, polypropylene fibers, and so on. Okay. So most of these topics will be discussed in future lectures. So question of scale. If we look at the concrete in macro scale, okay, we see concrete as homogeneous materials. But in fact, we know already concrete has sand, has coarse aggregate, and also have cement paste. So if we look at the concrete in centimeter scale or meso level, concrete is not homogeneous. So we call that heterogeneous structures, because we can see aggregate and cement. If we look at the concrete using SEM or scanning electron microscope, we look at the concrete in microstructure level in the scale of micrometer or even nanometer, then the structure of concrete and cement paste will change again. So for example, you can see this topomurite-like sheets. This is the mineral, we call that topomurite, which is very similar to the hydration product of Portland cement. So that's the layered structure of Portland cement paste. So in order to better design concrete in the micro level, okay, we need to study and understand the concrete in the micro scale and the meso scale. Okay, so that's the main purpose for this class. All right, so that's the short introduction of concrete. What is concrete? What is the major materials in concrete? The second part of this lecture will discuss cement chemistry. So the major chemicals inside the concrete. Okay. So before we do that, we'll discuss what is hydraulic cement, what is so-called non-hydraulic cement, how to manufacture cement, the major cement composition, the chemicals inside cement, different type of cement, how to blended cement and a special cement. Right. So this is ancient cement chemistry. The ancient Egyptians and ancient Roman use. All right. So 5,000 years ago, this is the ancient Egyptians used this to build the pyramid. Okay. So they use calcinating impure gypsum. So gypsum is calcium sulfate with 2 parts of water. So we heat gypsum into 130 degrees Celsius, and the gypsum will decompose into calcium sulfate with half water. So we call that calcium sulfate hydrate, and it will release 3 parts of water. Okay, so this calcium sulfate hydrate will be grounded into powder. Okay, so that's the second reaction. So this powder form calcium sulfate hydrate will mix with water again, and then as we can see, it will form gypsum. Gypsum has kind of strength, not as strong as modern concrete, but is strong enough to hold the rocks between inside the pyramid. Okay, so this is the ancient cement Egyptians use. So ancient Roman, they use another type of concrete. It's called lime mortar or air mortar. So calcium carbonate or CEEE688. So this is also limestone. Okay, so they heat limestone at very high temperature. As you can see, this is 1,000 degrees Celsius, much higher temperature compared with the 130 degrees Celsius ancient Egyptians use. So the limestone will decompose into calcium oxide and release the CO2. Okay, the calcium oxide is also called lime. Okay, they grounded lime into fine powder and mix with mortar. They kind of have a paste again. So calcium oxide powder with water, it will generate calcium hydroxide. Okay, calcium hydroxide react with CO2, which is coming from air, will form limestone again. This is why they call that air mortar, because they use the CO2 from the air. So the calcium hydroxide will become limestone. So limestone is much stronger compared with the gypsum. Okay. Also, if you generate some of the water, eventually the water will evaporate to the air. So the ancient concrete, ancient Roman use has stronger, higher strength compared with the ancient Egyptian use. Okay, this is the gypsum. This is limestone. Okay. So limestone and gypsum actually is not totally resistant to water. Okay. Let me show you the chemical reactions of this. Okay. Okay, so let me show you how limestone will react with water. So the CaCO3 limestone is not easy to be dissolved in water, but over time, limestone CaCO3 will react with water plus CO2 coming from the air. It will generate so-called calcium bicarbonate. Okay, so this is not water resistant. Okay, so slowly over time, limestone may be may be dissolved into in water. All right, so then come back to non-hydraulic cement and hydraulic cement. So the so-called non-hydraulic cement, the product is formed by combination, such as the concrete used by ancient Roman and ancient Egyptians. But it is not resistant to water, as I just showed you. Okay, but it may be made water resistant by adding pozzolanic materials. We'll discuss about this in future lectures, so don't worry about that. Hydraulic cement is defined as hardened by reacting with water, and the hydration product is water resistant. Okay, for example, the modern Portland cement, the concrete, the cement we use today. Okay, so Portland cement is a type of hydraulic cement made by pulverizing ground the clinker, consisting of hydraulic calcium silicate. Okay, we'll discuss how we can make Portland cement in a moment. All right, so here shows a little history about hydraulic cement. The first natural hydraulic cement is found in England, invented in England, so 1796. It's made by calcinating nodules of impure limestone and clay. Okay, so limestone, the major chemical in limestone is calcium carbonate. In clay, it has silica oxide, maybe some aluminum oxide, maybe some calcium oxide. Okay. 1813, Vicat is a French chemist. So he produced artificial hydraulic lime with synthetic mix of limestone and also clay. Okay. So the worst Portland cement coming by Joseph Asperdin in 1824. Okay. The reason we call that Portland cement is because the color. Okay. The color of Portland cement is very similar to the stone coming from Portland in England. Okay, so he used calcinated limestone mixed with clay and also heat it up to drive off the CO2. Okay, then ground the mixture into fine powder form. All right, so here shows the picture of a stone coming from the small island of Portland in England. So this is a stone from Portland in England. And this is a cylinder of modern concrete. Okay. Again, the reason we call them Portland cement is because the color of these two are very similar. Okay, nothing more. how we can make Portland cement? Okay, so the major steps to produce cement. First, we need to obtain the raw materials from limestone, from clay. We need 4 major raw materials: lime, iron, silica, and aluminum. Okay, so if you take the first letter from each of the words, you got LISA or Lisa. So, have you remember? We need lime, which is calcium oxide, iron, which is ferric oxide, silica oxide, and also aluminum oxide. Okay, so we need these raw materials from limestone, from clay. We prepare them, okay, mostly grind them into smaller size, and then we burn these materials in a large oven. We call that clinker. We call that clinkering process or burning process. So finally, we ground this clinker into fine powder. So here is a picture of quarry where we get our raw materials. The source of raw materials, remember, we need 4. So calcium, iron, silica, and aluminum. Okay, you can see we also have the 5th raw materials, sulfate. Okay, so why we need sulfate beside the top 4? Okay. So we'll discuss that in a moment. Okay, so let's look at the source of these raw materials. So for calcium, we can use limestone, which is the natural source, or we can use some byproduct, such as cement kiln dust or slag. So slag is industry byproduct of the steel producing process. Okay. So for iron, it can come in from clay or iron ore or other type of minerals such as shell. Silica can also come in from clay, which is the natural source. Flash is a major industry byproduct of coal burning process. So flash is also called coal ash. Okay. We can also use slag to produce the silica needed for cement production. Okay. For aluminum, we can also use clay, flash, and slag, shell, okay, or other natural and man-made materials. Okay. So sulfate is mainly coming from gypsum. All right. So let's look at a short video from PCA. So PCA is called Portland Cement Association. Okay. So PCA video on cement production.
Portland cements are manufactured by a process that begins by combining a source of lime, such as limestone, with silica and alumina, usually from clay, and a source of iron oxide, such as iron ore. The selected raw materials are then crushed, blended, and burned in a kiln to produce clinker. Once cooled, the clinker, with a small amount of gypsum added to regulate the setting time of the cement, is ground in a mill to produce the extremely fine gray powder called Portland cement.
Okay, so the first step is we need to get the raw materials from a quarry. Okay, so limestone, shell, clay. Okay, so the stone is reduced to a smaller size, from 5 inch to less than 1 inch, and stored. Okay. So the second step is the raw materials need to be grounded into powder and blended accordingly. Okay. So limestone, clay, sand, iron ore, okay, are proportioned and grounded into smaller size. Okay. In the second step, we have 2 types of processes. The dry process and the wet process. So the difference between these 2 processes is for the dry process, no water is added. For that process, water is added to facilitate the grounding process. Okay. For modern Portland cement production plant, mostly dry process will be used. So this is the newer method, the dry process. So after the raw materials are mixed, they will blend it into silos and grounded raw materials into storages before they go into the next step, which is the burning process inside the kiln. Okay, so this is the kiln, which is a huge oven with very high temperature inside it. The kiln is slowly rotated. Okay, so the speed of the rotation is very slow. Is about, let me see. All right. So the size of the kiln, the diameter of the kiln is around 20 feet or more, and the length of the kiln is around 500 to 600 feet. Okay, so very big, and you can see there's a slope inside the kiln. So the raw material is coming from the higher end and slowly going to the lower end, and inside the kiln, the clinker will be generated. Okay, so we will look at the details in the next slides. Okay. So materials coming from the kiln is called clinker. So the clinker will mix with the gypsum and further grounded in the next step, which is the step 4. So the clinker with gypsum is grounded into fine powder, and we call that Portland cement. Okay. All right. Okay. So here shows the picture of quarry. So the larger stones will be crushed into smaller size. So this shows the crushing process. Okay, and then different raw materials will be blended. Okay, before going to the kiln. Okay. This is overview of the cement plant. So the first one is the raw materials blending and storage. And here is the raw materials is grounded into smaller size. We also have suspension preheaters before the raw materials go into the kiln, which is here. Okay. So raw material going to the higher end of the kiln, and then coming out of the lower end of the kiln is the clinker. So here shows the clinker storage. And then clinker will be blended with gypsum and grounded into cement here. Okay. So the larger picture of the kiln, as you can see, is it's very, very big. Another picture of the kiln. So the rotational speed of the kiln is very slow. For every hour, it will only rotate like a 60 revolution. So 1 revolution for 1 minute. So slowly rotated. All right. So the burning process, the process in the kiln will generate a lot of pollution. Okay. And also use a huge amount of energy because the temperature inside the kiln is very high. Okay. So in fact, to produce 1 ton of cement, 1 ton of CO2 will be generated. Okay. So about 7 to 10% of the total man-made greenhouse gases coming from production of cement. Okay. So a lot of air pollution, a lot of energy is generated. So schematic of cement production. Okay, again, we have raw materials such as limestone, clay, and shale. They provide different raw materials: calcium oxide, silica, aluminum, and ferric oxide. Okay, they ground it and store together. They go into the preheaters before going to the burning kiln. Okay. Inside the kiln, cement compounds such as C3S, C2S will be generated. And then gypsum will be added into the clinker for final grinding. All right, here shows the what happened inside the kiln. Okay, so the raw materials is faded on the higher end. Okay, depending on the temperature. Okay, so we can see the gas temperature or the feed or the raw material temperature. So the temperature zone, so the temperature increase from 450 to more than 1500 degrees Celsius. Okay, so the first zone is called dehydration zone. The water is evaporated, CO2 is generated because the clay will decompose and release this CO2. And then the calcination zone, where limestone will decompose and release CO2. At the lower end of the calcination zone, we'll have initial formation of C2S. Okay, we'll talk about this in a moment. So C2S is one of the major compound of cement. And then we have the clinkering zone, which is between 1350 to 1550 degrees Celsius. So where the formation of melt, the melt is a combination of C3A and C4AF, other compound will be discussed in a moment, and also formation of C3S. Okay. All right, clinker is out of the lower end of the kiln. So look at the clinker picture on the left. It's like a chocolate. Okay, the size about 3/4 of inch, rounded shape. The gypsum, calcium sulfate with 2 parts of water, is added with clinker to control the hydration speed of one of the major chemical, which is C3A. Okay, so here just remember we need gypsum to slow down the chemical reaction of cement with water. Okay. All right, so how we can deliver cement?
Portland cement is available as a bulk powder or in waterproof bags. Most Portland cements are shipped in bulk using closed tanker trucks, covered rail hopper cars, rail tank cars, covered barges or ships with closed compartments. Pneumatic loading and unloading of the transport vehicle is the most popular means of handling bulk cement.
All right, so delivery of cement and the storage of cement.
Portland cement is a moisture-sensitive material. If kept dry, it will retain its quality indefinitely. Cement stored in contact with damp air or moisture sets more slowly and has less strength than Portland cement that has been kept dry. The relative humidity in a warehouse or shed used to store bagged cement should be as low as possible. Cement bags should not be stored on damp floors, but should rest on pallets. Bags should be stacked close together to reduce air circulation, but should never be stacked against outside walls. Where a shed is not available, bags should be placed on raised wooden platforms at least 4 to 6 inches above the ground. Waterproof coverings should fit over the pile and extend over the edges of the platform to prevent rain from reaching the cement and platform.
So we need to keep the cement dry before we actually use the cement. Otherwise, it will react with the moisture. Okay. Right. So here is the very important slides for this class. So typical oxide, or we call that constituent materials of cement. Again, we have lime, silica, alumina, and ferric oxide. Okay. So oxide, CaO, in cement chemistry, typically we use C. It is the shorthand for calcium oxide. The reason we use shorthand is because if we do not use that, the name of the chemical will be too long. Okay. So here in cement chemistry, we use C for calcium oxide. Okay. Typical weight of lime around 60%. For silica oxide, the shorthand is S. Okay. So again, this is very, very important. So S is for silica oxide. It is not the atom of sulfur. Okay. Alumina oxide, we use shorthand of A. Ferric oxide, we use F. A minor oxide is magnesium oxide, we use M here. Okay. Some even minor materials such as carbon dioxide, Ca2, we use C with a dashed line on top of it. For water, H2O, we use H as the shorthand. And for sulfur trioxide, SO3, we use S with a dashed line on top of it. Okay, so remember the shorthand for different type of oxide. Again, this is very important. Right, so this is the major oxides. Here shows the major compound, or we call major composition. So compound is a combination of 2 or 3 types of oxide, as we discussed in the previous slides. For example, tricalcium silicate has 3 parts of calcium oxide with 1 part of silica oxide. So the shorthand is C3S. Okay. The second type is called dicalcium silicate. It has 2 parts of calcium oxide with 1 part of silica oxide. So C2S. So C3A is for tricalcium aluminate, has 3 parts of calcium oxide with 1 part of aluminum oxide. The fourth one is C4AF, 4 parts of calcium oxide, 1 silica, and 1 ferric. Gypsum, so calcium sulfate, 2 water. So C is for calcium oxide, S with the dash line is S for SO3. H2 here means 2 parts of water. Again, if you remember the shorthand, okay, so you will know what this means. Okay. So try to spend some time remember the information from these 2 slides. For tricalcium silicate, that's another name, A-lite. A-lite is C3S with some impurities, such as magnesium oxide. Similarly, sometimes we also call C2S B-lite. So B-lite is C2S with some impurities. All right. So this is some new information we haven't learned from CEEE688, I believe. It is called bulk calculation. It is a formula which is not very accurate to calculate the percentage of the compounds such as C3S and C2S from the percentage of oxide. Okay. Why we cannot measure the compound directly? It is harder to measure the percentage of the compound such as C3S, but it is much easier to measure the percentage of oxide using XRF, which is X-ray fluorescence spectroscopy. Okay. So the purpose for bulk calculation is, make things easier to estimate the percentage of the compound, C3S to C2S and so on, from the oxide. Okay. So there are some of the assumptions, which is listed here. You can just read it. Okay. You are not required to totally understand the meaning for these assumptions. This is just for your information. Depending on the ratio of A to F, again, A is for aluminum oxide, the shorthand, and F here is for ferric oxide. So if the ratio is larger or equal to 0.64, we use this set of equation. If A to F ratio is less than 0.64, we use this equation. Okay. Remember, this is shorthand, C3S, and this is C is for calcium oxide. Okay. So based on the equation, these two sets of equation, we can easily estimate the percentage of the compound, but it's not very accurate. Okay. So here's some consideration about bulk calculation. Okay. So the relative proportion of C3S and C2S are very sensitive to calcium oxide content. Okay. So a small percentage of difference in calcium oxide will affect calculation quite a lot. Okay. And the bulk calculated percentage of C3S is relatively lower compared using other methods such as XRD. Okay, and this is some notes about calculation of C3A percentage. Okay, that's some other method, some other equation exists, but by far the most commonly used equation is this, the bulk calculation. So beside the bulk calculation, which estimate the compound percentage from oxide percentage using XRF, we can use some other method, such as this. This is called a photo micrograph. Okay, so we get a picture of clinker. We polish the surface of the clinker, and then we take a picture of that, and by counting the pistons or the areas for each faces. For example, C3S is the angular grid shape like this, and the dark color round shape is C2S, and anything in between C3S and C2S is the mixture of C4AF and C3A. So by measuring the areas of different phase and look at the picture of the clinker, we can also estimate the percentage of the compound. Okay. Here shows the picture of C3S, okay, which is light crystals like this, and C2S is the darker rounded crystals. This is a C2S. Okay. Right picture shows the SEM or scanning electron microscope of A light or C3S. Okay, so the angular shape crystals is C3S. All right. We can also use X-ray diffraction to analyze the major compounds such as C3S and C2S, but it is not very easy. Okay, in this class, just remember we could use X-ray diffraction method to measure the compound, but because the peaks of the different compound will overlap, so that will make the quantification very difficult. In later lectures of this class, we'll discuss how we can use X-ray diffraction to analyze the chemicals inside the samples. Okay. So this is another picture of using X-ray diffraction to measure the different compound. So here A is for A light, B is for B light, or C2S. Okay. All right, so here just say the limitation of X-ray diffraction. As I said, it is very hard and very challenging to quantify the percentage of a compound use X-ray diffraction. All right, so the typical Portland cement grain, as I showed in the picture on the left, is grayish color. Okay, if we look at the cement using SEM, you can see it has the small fine particles. The average size of cement particles is around 10 micrometer. Okay. All right. So the key idea for this lecture is, how concrete as a building material compared with steel and aluminum. Okay. What is the pros and cons of concrete compared to others? Okay. And concrete must be understood at microstructure and mesostructures. So this is what we trying to learn from this class, so we can better design and apply concrete in the micro scale. Okay. So what are the raw materials used to produce cement? So that is easy. That's LISA, L-I-S-A. Okay. So why cement need to be kept dry? Because without, if a cement is mixed with moisture, it will hydrate. The second lecture, Wednesday this week, we'll discuss how cement will react with water and it will generate what type of chemicals. So what are the major oxide or constituent materials in cement? Okay, so what are the major compound in cement? So constituent material is oxide, such as calcium oxide. Compound is, we talk about C3S, C2S, C3A, and C4AF. So go back to the 2 slides talking about the oxide and the compound and trying to remember the shorthand. And finally, how to use bulk calculation to estimate the percentage of compound using the oxide. Right, so this is some reading assignment for using the textbook. But again, the focus is on the slides, the handout here. Okay, so that's the end for this class. Any questions? Any questions before we dismiss for today? All right, so nice to meet you guys. I will see you Wednesday this week. All right, take care.
Thank you, Professor.
Okay, thank you. Bye.
Thank you. Bye-bye.
Bye.
Thank you.
Thank you.